I've been thinking a lot about infinity lately, and specifically about whether the universe itself might actually be infinite. You know, it's one of those questions that seems almost simple at first, like something you could answer in a sentence or two. But the more you dig into it, the more you realize it's actually one of the most profound and unsettling questions we can ask about reality. And what makes it even more interesting is that we might never know the answer for certain. We might be living in an infinite cosmos right now, and there's a very real possibility we'll never be able to prove it one way or the other. That's both humbling and kind of beautiful, isn't it? The idea that there are limits to what we can know, even with all our telescopes and mathematics and centuries of careful observation. So let me start with something that might seem obvious, but is actually crucial to understand. When we talk about the universe being infinite, what do we actually mean? Because infinity is one of those concepts that we throw around casually, but when you really think about it, it's almost impossible to truly grasp. I mean, genuinely grasp, not just intellectually understand the definition, but really feel what it means in your bones. An infinite universe wouldn't just be really, really big. It wouldn't be the biggest thing you could imagine, and then some. It would be limitless, no edge, no boundary. No matter how far you traveled, you could keep going forever and never reach an end. And that's strange, right? Because everything in our everyday experience has limits. Every room has walls. Every journey has a destination. Every book has a final page. But an infinite universe, it just keeps going and going and going forever. Now here's where things get interesting right away. When astronomers talk about the universe, they're usually talking about the observable universe. And that's a really important distinction, one that trips people up all the time. The observable universe is the part of the cosmos that we can, in principle, see. It's the region of space from which light has had enough time to reach us since the Big Bang. And that's finite. We know how big it is, roughly. About 93 billion light years in diameter. Yes, 93 billion, even though the universe is only about 13.8 billion years old. That's because of expansion, but we'll get to that in a bit. The point is, the observable universe has a size we can measure and comprehend, at least mathematically. But the observable universe is just that, observable. It's like standing in the middle of a vast, dark field at night with a flashlight. The circle of light around you has a clear boundary where the darkness begins, but that doesn't mean the field ends there. The field might stretch on for miles beyond your light, or it might stretch on forever. Your flashlight doesn't tell you where the field ends, it only tells you how far you can see. And that's exactly the situation we're in with the universe. We can see out to a certain distance, a cosmic horizon defined by the speed of light and the age of the universe. But beyond that horizon, we simply don't know. The universe could end just past our view, or it could continue infinitely in all directions. And this is where the real mystery begins, because there's good reason to think it might continue forever. Several reasons, actually. Let me take you through them, and fair warning, some of this is going to feel counterintuitive. The universe has a way of defying our everyday intuitions, of working in ways that seem impossible until you understand the underlying principles. And even then, even after you understand the math and the observations, it still feels impossible. That's just how it is with cosmology sometimes. The first big clue that the universe might be infinite comes from its geometry. And I know that sounds abstract, but bear with me because this is actually one of the most elegant discoveries in all of science. You see, space itself has a shape. Not in the sense that it looks like a sphere or a cube, but in a mathematical sense. It has curvature. And that curvature can be positive, negative, or flat. Think about it this way. Imagine you're a tiny two-dimensional creature living on the surface of a sphere, like an ant on a basketball. If you draw a triangle on that curved surface and measure the angles, they'll add up to more than 180 degrees. That's positive curvature. Now imagine you're on a saddle-shaped surface instead, curving downward. Draw a triangle there, and the angles add up to less than 180 degrees. That's negative curvature. But on a flat surface, like a piece of paper, the angles add up to exactly 180 degrees. That's flat, or zero curvature. Our universe works the same way, except in 3 dimensions rather than 2. And here's the remarkable thing. When scientists use satellites like WMAP and Planck to measure the geometry of the universe by looking at the cosmic microwave background radiation, the afterglow of the Big Bang, they find that space is flat. or at least it's flat to within a tiny margin of error. We're talking flat to better than 1% precision. The angles of cosmic triangles add up to exactly what Euclidean geometry predicts they should. And this flatness, this perfect flatness, has profound implications. Because here's the thing, if the universe has positive curvature, it could be finite but unbounded like the surface of a sphere. You could travel forever in one direction and eventually come back to where you started, like circumnavigating a globe. But a flat universe is almost certainly infinite. Not definitely infinite, technically speaking, because you could imagine some exotic topology where even a flat space wraps around on itself. But the simplest interpretation, the one that doesn't require any special pleading or unlikely configurations, is that a flat universe extends forever in all directions. It has no edge, no center, no boundaries whatsoever, just space continuing uniformly in every direction without end. And when you think about that, really think about it, it's staggering. It means that if you could somehow travel fast enough, far enough, you could keep going past trillions upon trillions of galaxies, through cosmic voids larger than anything we can observe, past structures we've never seen and never will see, and you would never run out of universe. There would always be more, always another galaxy cluster, always another supercluster, always more stars, more planets, more space, forever. It's almost too much to hold in your mind. But let's dig deeper into why the universe is flat in the first place, because that's a question that bothered cosmologists for decades. You see, flatness is actually an unstable state in the early universe. Let me explain why. In the first moments after the Big Bang, the universe was expanding rapidly, and if it had even the tiniest deviation from perfect flatness, even one part in a trillion, that deviation would have grown exponentially over time. A slightly positively curved universe would have quickly curved back on itself and collapsed. A slightly negatively curved universe would have opened up rapidly into an endless empty expansion. But we see flatness, perfect flatness. How? The answer that most cosmologists accept today is inflation, cosmic inflation. And this is one of the most important ideas in modern cosmology, even though it's also one of the most speculative. The idea is that in the first tiny fraction of a second after the Big Bang, something like 10 to the minus 35 seconds, the universe underwent a period of incredibly rapid expansion, not just rapid, exponential. The fabric of space itself expanded faster than the speed of light, doubling in size over and over again in the tiniest fractions of time. During this inflationary period, any initial curvature would have been stretched out, flattened, in the same way that the surface of a balloon looks flatter and flatter as you blow it up bigger and bigger. Stand on Earth and the ground looks flat, right? Even though you're on the surface of a sphere. That's because Earth is so large compared to your perspective that the curvature becomes negligible. Inflation did the same thing to the universe, stretching it so enormously that any curvature became immeasurably small. But here's where it gets even more interesting. Inflation doesn't just explain why the universe is flat. It might also explain why the universe is infinite. Because if inflation happened, if space really did expand exponentially in that first instant, then the universe would have become vastly, incomprehensibly larger than the observable region we can see. Think about it. During inflation, space expanded by a factor of at least 10 to the 26th power. Some models suggest much more. That means the observable universe, the part we can see, might be just a tiny infinitesimal speck in a much vaster cosmos. And if the universe was infinite before inflation began, it would still be infinite after. Inflation doesn't change that. It just makes the infinite even more vastly infinite. And that raises a fascinating question. Could the universe have been infinite even before inflation? Could it have been infinite from the very beginning, from the Big Bang itself? This is where things get philosophically deep, because we're asking about the nature of the Big Bang. And the Big Bang is one of the most misunderstood concepts in cosmology. Most people picture it as an explosion, a point in empty space that suddenly erupted outward. But that's not what the Big Bang was. The Big Bang wasn't an explosion in space. It was an expansion of space. Space itself was expanding, carrying galaxies along with it, like raisins in rising bread dough. And if space was infinite to begin with, then even at the moment of the Big Bang, even when everything was compressed to incredible density, there would still have been infinite space. just infinite space that was infinitely dense. I know that sounds contradictory. How can something be both infinite and compressed? But that's the thing about infinity. It breaks our intuitions. An infinite universe could have been infinitely dense and infinitely hot at the Big Bang, and then expanded to become infinitely large and much less dense. Both states are infinite. The infinity doesn't change. What changes is the density, the temperature, the distance between any 2 points. And this is actually consistent with what we observe. When we look at the cosmic microwave background, the radiation left over from the Big Bang, we see that it looks the same in every direction. The universe is homogeneous and isotropic at large scales. Every region looks like every other region, statistically speaking, and that uniformity is exactly what you'd expect from an infinite universe with no center and no edge. But I want to pause here and address something that might be bothering you. If the universe is infinite, does that mean there's an infinite amount of stuff? Infinite galaxies, infinite stars, infinite planets? And if so, doesn't that lead to all sorts of weird implications? Like the idea that somewhere out there, infinitely far away, there's an exact copy of you, living an identical life? Or even stranger variations, every possible version of you that could exist? And the answer is yes, sort of. It depends on what you mean by infinite and what you assume about the distribution of matter. Let me walk you through this carefully because it's one of the most mind-bending implications of an infinite universe. If space is truly infinite and matter is distributed uniformly throughout it, then yes, there would be an infinite number of galaxies, an infinite number of stars, an infinite number of planets, and because there are only a finite number of ways that atoms can be arranged into the size of an observable universe. If you go far enough, probability dictates that patterns must repeat. It's like flipping a coin. If you flip a coin a finite number of times, you get one sequence of heads and tails. But if you flip it infinitely many times, every possible sequence will occur, not just once, but infinitely many times. There would be regions of space unimaginably far away where the arrangement of matter is identical to our observable universe down to every last atom. There would be copies of Earth, copies of you, reading these exact words at this exact moment. But before you get too existentially dizzy, remember that this depends on some big assumptions. It assumes perfect uniformity in the distribution of matter, which might not be true. It assumes the laws of physics are the same everywhere, which they seem to be as far as we can tell, but we can't be certain beyond our observable horizon. And it assumes quantum randomness eventually produces every possible configuration, which is probabilistically true but happens on scales so vast they're essentially meaningless to us. These doppelgangers, if they exist, would be so far away that we could never reach them, never communicate with them, never know they're there. They're beyond our cosmic horizon and always will be, because the universe is expanding and those distant regions are receding from us faster than light can travel between us. And that brings up another crucial point about infinity and expansion. The universe is expanding. We've known this since Edwin Hubble's observations in the 1920s, when he discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. And not only is the universe expanding, but the expansion is accelerating. This was the shocking discovery in the late 1990s that won the Nobel Prize. Some mysterious force, something we call dark energy, even though we don't really know what it is pushing the universe to expand faster and faster over time. Now, you might think that expansion contradicts the idea of an infinite universe. If the universe is expanding, doesn't that mean it must be growing from a finite size? But no, that's not how it works. An infinite universe can still expand. Remember, expansion isn't about the universe getting bigger in some external space. There's no outside. The universe is all there is. Expansion means that the distance between any 2 points in space is increasing over time. If the universe is infinite, then it was infinite yesterday, it's infinite today, and it'll be infinite tomorrow. Expansion just means that the infinite space is stretching, that the density of matter is decreasing as galaxies move farther apart. But infinity remains infinity. You can't make infinity bigger. It's already as big as it could possibly be. And here's something truly wild about this accelerating expansion. In the far future, billions of years from now, distant galaxies will be receding from us so fast that their light will never reach us. Our cosmic horizon will actually shrink in terms of what we can see. Galaxies that we can observe today will disappear beyond the horizon, their light redshifted into invisibility. Future civilizations, if any exist, will look out into space and see far fewer galaxies than we see now. They might even conclude that their galaxy is alone in an empty universe, that there's nothing else out there. They'd be wrong, of course. There would be countless galaxies beyond their view, but they'd have no way to know that. No evidence to contradict their isolation. It's a sobering thought. We live in a special time, cosmologically speaking, when we can still see evidence of the Big Bang and observe the large-scale structure of the universe. That window won't be open forever. But let's return to the question of whether the universe is actually infinite, because so far I've been talking about why it might be, but I haven't addressed the fundamental uncertainty. The truth is, we don't know. We can't know, at least not with our current technology, and perhaps not ever. All of our observations are limited to the observable universe, the region within our cosmic horizon. We can measure the curvature of space within that region, and we find it's flat. But that doesn't prove the entire universe is flat. It proves that the observable part is flat, which means if there is curvature, it's on a scale larger than we can measure. The universe could be positively curved, meaning finite, but so enormous that the curvature is undetectable within our observable patch. Imagine being that ant on the basketball again, but now the basketball is the size of the solar system. You'd measure your local surface as flat too, because the curvature would be too gradual to detect over short distances. So we're left with a situation where both possibilities remain open. The universe could be infinite, extending forever with no boundary, or it could be finite but unimaginably vast, far larger than the part we can observe. And honestly, I'm not sure which possibility is stranger. An infinite universe means there's no totality, no whole, no complete picture we could ever grasp. It means the cosmos is fundamentally beyond human comprehension in its scale. But a finite universe raises its own questions. If the universe is finite, what's beyond it? Nothing, not even empty space. How do you define the edge of existence? What does it mean for something to be finite if there's no outside to contrast it with? These questions troubled philosophers and scientists for centuries before we had modern cosmology. Ancient Greeks debated whether the cosmos was finite or infinite. Some argued that infinity was impossible, that everything must have limits. Others argued that the idea of a boundary was absurd. If you reach the edge of the universe and throw a spear, does it stop at the boundary or fly through? If it stops, what stops it? If it flies through, then the boundary wasn't really the edge, was it? These paradoxes don't have easy answers, and in some sense, modern cosmology hasn't fully resolved them. We've just reframed the question in terms of geometry and topology rather than philosophy. But there's another angle to consider, another reason the universe might be infinite, and this one is even more speculative. It has to do with the multiverse. Now, I know the multiverse is a controversial idea, and many physicists are skeptical of it, and for good reason. It's not directly testable. We can't observe other universes by definition, because if we could observe them, they'd be part of our universe. But the multiverse arises naturally from certain theories, particularly the theory of eternal inflation I mentioned earlier. Here's how it works. Remember, inflation, that period of rapid expansion in the first fraction of a second after the Big Bang. Well, in many models of inflation, it doesn't just happen once and stop everywhere at the same time. Instead, inflation ends in some regions of space while continuing in others. Imagine a pot of boiling water. Bubbles form in different places at different times. Each bubble is a region where inflation has ended and a normal expanding universe forms. But between the bubbles, space is still inflating, still expanding exponentially, and it will keep inflating forever, spawning more and more bubbles, each one a separate universe with its own Big Bang, its own physics potentially, its own infinite or finite extent. In this scenario, our observable universe is just one bubble among infinitely many. The multiverse as a whole is infinite, and it's eternally generating new universes. Each universe might itself be infinite or finite, depending on the details. But the multiverse, the totality of all existence, would be infinite in both space and possibility. Every universe that can form does form, somewhere in the eternally inflating bulk. And that's a staggering thought. It means our entire observable cosmos, with its hundreds of billions of galaxies, is just one tiny bubble in an infinite foam of universes, most of which we can never observe or interact with. Of course, this is speculative. Eternal inflation is a consequence of certain models, but we don't know if those models are correct. We don't know if inflation really happened at all, though the evidence is pretty strong. And even if it did, we don't know if it continues eternally in some regions or ended everywhere at once. These are open questions. But the fact that serious scientists take these ideas seriously tells you something about how far cosmology has come. We're asking questions that would have seemed like pure fantasy a century ago. We're probing the ultimate nature of reality with mathematics and observations and trying to figure out whether existence itself is infinite. And there's yet another way the universe might be infinite, or at least effectively infinite, and this one comes from quantum mechanics. If you've ever heard of the many worlds interpretation of quantum mechanics, you might be familiar with this idea. In quantum mechanics, particles don't have definite properties until they're measured. Before measurement, they exist in a superposition of all possible states. Schrödinger's famous cat is both alive and dead until you open the box. And in the many worlds interpretation, every possible outcome of a quantum measurement actually happens, but in different branches of reality. When you measure a particle's spin and find it's up, there's another branch where you found it down. Every quantum event splits reality into multiple branches, and this has been happening since the Big Bang, creating a tree of diverging timelines that grows more complex with every passing moment. If this interpretation is correct, and again it's controversial, then there are infinitely many versions of reality, infinitely many branches, each one as real as the one we experience. And in that sense, existence is infinite even if any individual universe is finite. The multiverse of quantum branches would be infinite in possibility space, encompassing every way history could have unfolded. There would be branches where the dinosaurs never went extinct, branches where you made every decision differently, branches where the laws of physics are slightly different because the quantum fluctuations in the early universe played out differently. It's infinity of a different kind, not spatial infinity, but a sort of probability infinity, an infinite branching tree of realities. But let's ground ourselves again, because these speculations can spiral pretty quickly into philosophy and metaphysics. Let's return to the observational evidence, the hard data we have about our actual universe. What can we measure? What do we know for certain? We know the universe is expanding. We know it's about 13.8 billion years old. We know it's filled with dark matter and dark energy, mysterious substances we can detect through their gravitational effects but don't fully understand. We know the observable universe contains at least 2 trillion galaxies, probably more. We know the cosmic microwave background radiation is uniform in all directions to 1 part in 100,000, with tiny fluctuations that seeded the formation of galaxies. And we know that space, as far as we can measure, is flat. All of these observations are consistent with an infinite universe, but they don't prove it. They're also consistent with a finite universe that's much larger than we can observe. The honest answer is that we're living in a profound state of uncertainty about one of the most basic facts about reality. And there's something beautiful about that uncertainty, something humbling. Here we are with all our technology, all our accumulated knowledge, all our sophisticated mathematics and powerful telescopes, and we still don't know if the universe goes on forever or eventually ends. We're like ancient explorers who've mapped the coastline of their known world but have no idea if there are more continents beyond the horizon. Except our horizon is set by the speed of light and the age of the universe, and we can never sail beyond it. But even if we can't know for certain, we can think about what it would mean. What would it mean for us, for humanity, for our place in the cosmos, if the universe really is infinite? I think it would change something fundamental about how we see ourselves. We already know we're not at the center of anything. Copernicus taught us that Earth isn't the center of the solar system. Hubble taught us that our galaxy isn't the center of the universe, that there is no center. But an infinite universe takes that decentralization to its logical extreme. In an infinite universe, every point is equally far from the edges, because there are no edges. Every observer sees the same large-scale structure, the same patterns and distributions. There's no special place, no privileged location, no cosmic significance to any particular region of space, and yet paradoxically that might make our existence more meaningful, not less. Because if the universe is infinite, if there are infinite stars and infinite planets and infinite opportunities for complexity and life to arise, then the fact that we exist here, now, as conscious beings capable of pondering these questions, is both infinitely unlikely and absolutely certain. It had to happen somewhere, somewhen. The universe is so vast that even the most improbable events occur, not once, but infinitely many times. And we're one of those improbable events. We're the universe becoming aware of itself, matter organized in such a way that it can contemplate its own existence. Carl Sagan used to say we're made of star stuff, and that's literally true. The atoms in your body were forged in the nuclear furnaces of stars that lived and died billions of years ago. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was created in stellar cores and scattered across space when those stars exploded as supernovae. We're not separate from the cosmos. We're part of it, an integral part, a way for the universe to know itself. And if the universe is infinite, then that capacity for self-knowledge might exist in infinite forms across infinite expanses of space and time. We might be just one tiny node in an infinite network of consciousness, each node experiencing its own piece of the infinite whole. Of course, infinity also raises some troubling possibilities. If the universe is infinite and matter is distributed uniformly, then somewhere out there, impossibly far away, there are regions that are identical to our own. And I don't mean similar. I mean identical down to the last quantum state. There would be another Earth, another version of you, making exactly the same choices, thinking exactly the same thoughts, and not just one copy, infinitely many copies. And between those exact copies, there would be near copies, versions where one tiny thing is different. A version of Earth where you wore a different shirt today. A version where you didn't read these words. A version where humans never evolved. A version where life never formed at all. Every possibility, no matter how unlikely, occurs somewhere in an infinite universe. Does that make your choices meaningless? Does it diminish the significance of your life if there are infinite versions of you living out every possible variation? I don't think so. Each version of you experiences their own reality, their own continuity of consciousness. The fact that other versions exist doesn't change your subjective experience. You still make real choices that matter to you and the people around you. The existence of parallel versions doesn't erase the importance of this version, the one you're living right now. If anything, it emphasizes the preciousness of each moment, each decision, because even though similar moments might play out elsewhere, this particular moment is unique to your experience. But I'll admit it's disconcerting to think about. We like to feel that we're special, that our lives have unique significance. The idea that we're one of infinitely many copies can feel diminishing. But maybe that's just our ego talking, our stubborn resistance to accepting our place in the cosmos. The universe doesn't care about our preferences for specialness. It simply is what it is, whether finite or infinite, whether centered on us or indifferent to us. And there's a kind of freedom in accepting that. Once you let go of the need to be cosmically significant, you can focus on the significance that actually matters, the relationships you form, the experiences you have, the small ways you affect the people around you. Those things are real and meaningful, regardless of what the universe is doing on infinite scales beyond your reach. Let's talk about time for a moment, because infinity in space naturally leads to questions about infinity in time. If the universe is spatially infinite, has it also existed for infinite time? Will it continue to exist forever into the future? These are separate questions from spatial infinity, but they're related. We know the universe had a beginning, at least in the sense that there's a finite time in the past before which our physics breaks down, and we can't meaningfully talk about what happened. That's the Big Bang, roughly 13.8 billion years ago. But did time itself begin at the Big Bang, or was there something before? This is where we hit the limits of our current theories. General relativity, our best theory of gravity and space-time, predicts that time began at the Big Bang, that asking what came before is like asking what's north of the North Pole. It's a meaningless question because time itself didn't exist before. But many physicists suspect that general relativity breaks down at the extreme conditions of the Big Bang, that we need a theory of quantum gravity to really understand what happened. And some quantum gravity theories suggest that time might not have had a beginning after all, that the Big Bang was a transition or a bounce rather than an absolute start. Loop quantum cosmology, for instance, suggests that our universe might have emerged from a previous contracting universe that reached a minimum size and then bounced back into expansion. In that scenario, time extends infinitely into the past through an endless series of bounces, each one resembling a big bang from the perspective of observers in that cycle. String theory offers other possibilities, including scenarios where our universe is a brane, a lower dimensional surface embedded in a higher dimensional bulk, and the Big Bang was the result of brane collisions that might happen repeatedly over infinite time. These are speculative ideas, far from proven, but they illustrate that even the beginning of time might not be as definitive as we once thought. And what about the future? If the universe is infinite in space, will it also be infinite in time? Will it exist forever? Based on current observations, it looks like the answer is yes, though the far future of the universe is bleak. With dark energy driving accelerated expansion, galaxies will continue to drift apart. In about 100 billion years, all galaxies beyond our local group will have receded beyond the cosmic horizon, their light redshifted into invisibility. Stars will continue to form and die, but eventually the supply of gas will run out. In trillions of years, the last stars will flicker out, leaving a dark, cold universe filled with dead stellar remnants, black holes, and isolated planets. Even black holes will eventually evaporate through Hawking radiation, a process that takes an unimaginably long time, something like 10 to the 100 years. And after that, just an ever-expanding darkness, cold and empty, approaching absolute zero, with nothing happening anywhere ever. This is sometimes called the heat death of the universe, the final equilibrium state where entropy is maximized and no energy gradients exist to drive any processes. It's a deeply unsettling vision of the future, especially if the universe is infinite, because it means infinite space will eventually become infinite emptiness. All structure will dissipate, all complexity will unwind. The brief moment of interesting things happening, of stars and planets and life, will be an infinitesimally small blip in an infinite timeline of nothingness. We live in a cosmologically young universe, a time when there's still energy to concentrate, still matter to organize, still stars lighting up the sky. But that won't last, not in cosmological terms. Does that make everything meaningless? Does the eventual heat death of the universe imply that nothing we do matters? I don't think so. Meaning doesn't require permanence. A beautiful sunset isn't less beautiful because it fades. A symphony isn't less moving because it ends. The value of existence isn't measured by how long it lasts, but by the richness of what happens while it does. We're part of the universe during its most interesting phase, the phase where complexity emerges, where consciousness arises, where questions can be asked. That's a remarkable thing, regardless of what happens in the incomprehensibly distant future. But let's return once more to the question of spatial infinity, because I want to address a philosophical puzzle that's haunted thinkers for centuries. If the universe is infinite, can we say that infinity exists in a physical sense, or is infinity only a mathematical concept? This might sound like an abstract semantic debate, but it touches on something profound about the relationship between mathematics and physical reality. In mathematics, infinity is a precise concept. There are different kinds of infinity, actually. Countable infinity, like the set of natural numbers 1, 2, 3, and so on forever. Uncountable infinity, like the set of real numbers, which includes all the decimals between 0 and 1. And even larger infinities beyond that, hierarchies of infinite sets that Georg Cantor proved exist in the late 19th century. These mathematical infinities are rigorously defined and perfectly consistent. We use them all the time in calculations, in limits, in analysis. But mathematical infinity is an abstraction. It's a property of sets and series and functions, not of physical objects. So if the universe is infinite, does that mean physical infinity exists? Or is it just that the universe is so large that mathematical models describing it require infinite parameters? This might seem like splitting hairs, but it relates to a deep question about whether mathematics is discovered or invented. Are mathematical truths like the properties of infinity inherent features of reality that we discover, or are they mental constructs we invent to describe reality? If the universe is physically infinite, it suggests that at least some mathematical infinities have direct physical counterparts, that the universe itself embodies this abstract concept. On the other hand, we should be careful about taking our mathematical models too literally. Physics uses mathematics as a language, a tool for making predictions and organizing observations. But the map is not the territory. Just because our best models of the universe involve infinite space doesn't necessarily mean the universe is actually infinite. It might just mean that infinity is a useful approximation, a way of saying the universe is so large that finite models break down and infinite models work better. We do this all the time in physics. We use infinities as shortcuts when the actual numbers are impractically large. The surface of the Earth is finite, but for most purposes, we treat it as infinite because the curvature is negligible over short distances. Still, there's something compelling about the idea that the universe might embody mathematical infinity in a literal way. It would be a profound connection between abstract mathematics and concrete reality, a suggestion that the universe has properties that transcend our everyday intuitions about size and scale. And it would mean that infinity isn't just a useful fiction or a mathematical convenience, but an actual feature of the cosmos we inhabit. One more angle to consider, and this one brings us back to the question of what we can know versus what we can speculate about. Even if we can never prove the universe is infinite, we might be able to gather more evidence one way or the other. Future missions might measure the cosmic microwave background with even greater precision, looking for patterns that would indicate the universe wraps around on itself at large scales. If the universe is finite but very large, there might be subtle correlations in the temperature fluctuations of the CMB that would give it away, like seeing the same patterns repeated across the sky because light has traveled all the way around the cosmos. So far, we haven't seen such patterns, but our measurements aren't sensitive enough to rule them out if the universe is bigger than a certain size. There's also the possibility of detecting gravitational waves from the inflationary epoch. Inflation would have produced ripples in spacetime, primordial gravitational waves that are still propagating through the universe. If we could detect those waves and measure their properties, we might learn more about the inflationary process and whether it leads naturally to an infinite universe. Projects like LIGO and future space-based gravitational wave observatories might give us clues, though detecting primordial gravitational waves is extraordinarily challenging. And then there's the ongoing quest to understand dark energy, the mysterious force driving the accelerated expansion. If we can figure out what dark energy is and how it behaves, we might gain insights into the ultimate fate of the universe and whether its infinity, if it exists, is stable over time. Does dark energy remain constant, or does it change? Will the expansion continue accelerating forever, or will something else happen on timescales beyond our current observations? These questions are active areas of research, and the answers might shed light on the nature of cosmic infinity. But even with all these future observations, we might never know for certain. There might be fundamental limits to what we can learn about the universe beyond our cosmic horizon. If the universe is infinite, we're permanently restricted to observing a finite patch of it. We can never see the whole. We can never know if our local region is representative of the whole, or if there are variations and surprises beyond our reach. It's like trying to understand an infinite ocean by only examining the water within arm's reach. You can learn a lot about the local properties, the temperature, the salinity, the creatures living nearby, but you can't know if the ocean is the same everywhere or if there are vast regions utterly unlike your local environment. And maybe that's okay. Maybe the fact that we can ask these questions, that we can build telescopes and satellites and mathematical models to probe the edges of observable reality is enough. We're finite beings living finite lives in a universe that might be infinite, and there's something poetic about that. We can't grasp the whole, but we can marvel at our tiny piece of it. We can trace the patterns, follow the logic, see how far our understanding reaches, and acknowledge where it ends. That's the human condition in microcosm. We live in a world we can't fully comprehend, and yet we keep trying, keep pushing the boundaries of knowledge, keep asking, what's out there beyond the horizon? The question of whether the universe is infinite is ultimately a question about the nature of existence itself. It's not just about size or scale. It's about whether reality has boundaries or extends without limit. It's about whether there's a totality to things or if the very concept of a total universe is misguided. It's about our place in a cosmos that might dwarf us beyond all comprehension, or might, just barely, be within the realm of the knowable. And it's about the relationship between the physical and the mathematical, between what exists and what we can describe. Perhaps the most honest answer is that we don't know, and perhaps we can't know, but we have good reasons to think the universe might be infinite. The flatness of space, the theory of inflation, the uniformity of the cosmic microwave background, the absence of any detected edges or boundaries, all point toward an infinite cosmos. But infinity is such an extreme concept, so far beyond our everyday experience, that it remains difficult to accept emotionally, even when we accept it intellectually. Can something really go on forever? Can there be no end, no totality, no final reckoning of what exists? And yet the alternative is almost as strange. A finite universe would have an edge, or at least a topology that wraps around on itself, and either way, that raises questions that are hard to answer. What's beyond the edge? What does it mean for space to curve back on itself in ways we can't visualize? The universe, it seems, is strange no matter how you slice it. Infinite or finite, it defies our intuitions and challenges our understanding. So where does that leave us? Standing under a night sky, looking up at stars that are islands of light in an ocean of darkness, wondering how far it all goes. Does it end somewhere, or does it stretch forever? Are we alone in a finite cosmos, or are we one tiny spark in an infinite sea of possibilities? These are questions that touch on science and philosophy and spirituality all at once. They're questions about the ultimate nature of reality and our place in it. And maybe the point isn't to answer them definitively, but to sit with them, to feel the weight of the uncertainty and the wonder of the possibility. Because whether the universe is infinite or not, it's vast beyond our comprehension. It contains mysteries we'll never solve and beauties we'll never fully appreciate. And we're part of it. Not observers looking in from outside, but participants, beings made of the same stuff as stars and planets, governed by the same laws, shaped by the same cosmic history. We're the universe's way of knowing itself, and in that sense, every question we ask about infinity is the universe asking about itself. There's a humility in that realization, but also a strange kind of empowerment. We might be infinitesimally small compared to the cosmos, but we're also intimately connected to it. Our atoms were forged in stars. Our molecules were assembled in the chemistry of planetary surfaces. Our thoughts emerge from patterns of neural activity that depend on quantum mechanics and thermodynamics and all the fundamental forces of nature. We're not separate from the universe, we're woven into its fabric. And that means when we wonder about infinity, when we contemplate the boundaries of existence, we're engaging with the deepest questions reality can pose. So yes, the universe might be infinite. It might extend forever in all directions, filled with infinite galaxies and infinite stars and infinite possibilities. Or it might be finite, but so vast that we'll never see its edges, never know its full extent. Either way, we're living in an age when we can ask these questions seriously, when we have the tools to probe the cosmos and the theories to make sense of what we find. That's an extraordinary thing. For most of human history, these questions were purely philosophical. Now they're scientific. We can measure, we can calculate, we can test hypotheses against observations, we can narrow down the possibilities even if we can't eliminate them entirely. And in doing so, we're participating in one of the great adventures of human thought. We're pushing the boundaries of knowledge, exploring the edges of the knowable, confronting the limits of our understanding with courage and curiosity. We're asking what the universe is, how it came to be, where it's going, and whether it goes on forever or eventually ends. These are the kinds of questions that define us as a species, that separate us from other animals, that give meaning to our brief moment of consciousness in a vast and ancient cosmos. The universe might be infinite. We might live in a cosmos with no boundaries, no edges, no limits. A cosmos where every possibility eventually occurs, where patterns repeat infinitely, where the strange fact of our existence is replicated endlessly across unimaginable distances. Or we might live in a finite cosmos, bounded in some way we don't yet understand, smaller than infinity, but still unfathomably large. Either way, we're here, we're aware, we're asking questions. And that, in itself, is a kind of miracle. A brief flicker of complexity and consciousness in a universe that's mostly empty space and radiation, a moment of self-awareness in the long, slow unfolding of cosmic history. So when you look up at the night sky and wonder how far it goes, know that you're asking one of the deepest questions humans have ever pondered, and know that the answer, whatever it is, whether we ever find it or not, speaks to something fundamental about the nature of existence and our place in it. The universe might be infinite. And if it is, that's both humbling and magnificent. Humbling because it means we're vanishingly small in the grand scheme. Magnificent because it means reality is richer and stranger than we ever dared imagine. And we somehow get to be part of it, to experience it, to wonder about it. For a brief time, in this particular corner of space, the universe is asking itself if it goes on forever. And that question, that act of wondering, might be one of the most profound things happening anywhere in the cosmos. Because in asking, we're participating in the universe's journey toward understanding itself. We're infinity trying to comprehend infinity. We're the finite contemplating the infinite. And maybe that's what consciousness is for. Maybe that's why we're here, to ask the questions that reality itself can't answer without us. But let me take you deeper into this, because there are layers we haven't fully explored yet, nuances and implications that deserve more attention. When we talk about an infinite universe, we need to be really precise about what kind of infinity we mean. And this is where the mathematics gets fascinating and the philosophy gets thorny, because infinity isn't just one thing. It's a whole spectrum of concepts, each with different properties and implications. Consider this. When mathematicians talk about infinite sets, they distinguish between different sizes of infinity. Cantor's famous diagonal argument proved that the set of real numbers is a larger infinity than the set of natural numbers, even though both are infinite. The natural numbers, 1, 2, 3, 4, and so on, form what's called a countably infinite set. You can list them in sequence. You can match each one with a counting number. But the real numbers, all the decimals, all the fractions, all the irrational numbers like pi and the square root of 2, they form an uncountably infinite set. You can't list them all. There's no way to put them in order and count through them. Between any two real numbers, there are infinitely many more real numbers. It's a denser, richer kind of infinity. So which kind of infinity might the universe be? If space extends infinitely, is it like the natural numbers, countable in principle, or like the real numbers, uncountable and dense? This might seem abstract, but it has real implications. If space is continuous, if you can zoom in forever and always find more structure, more detail, then we're dealing with something like the continuum, the uncountable infinity. But if space is ultimately discrete, if there's a smallest possible unit of space, then even an infinite universe would be more like the natural numbers, countably infinite regions stacked next to each other. And this connects to quantum gravity again, because many approaches to quantum gravity suggest that space itself might be discrete at the Planck scale. The Planck length is about 10 to the minus 35 meters, an absurdly tiny distance where quantum effects and gravitational effects become equally important. Below that scale, our current theories break down. We don't know how to describe what's happening. Some theories, like loop quantum gravity, suggest that space is made of discrete loops or nodes, a kind of quantum foam where the smooth fabric of space-time we experience is just an approximation that emerges at larger scales. If that's true, then even an infinite universe would be built from a countable infinity of these fundamental units, each one distinct and separate. But other theories, like string theory, treat space as fundamentally continuous, at least in most formulations. In string theory, the basic objects are one-dimensional strings vibrating in higher dimensional space, and the extra dimensions can be compactified or extended, finite or infinite, depending on the model. Some versions of string theory allow for infinite extra dimensions, creating a kind of infinity within infinity, a cosmos where our three-dimensional space is embedded in a higher dimensional bulk that extends without limit in directions we can't perceive. And this raises yet another fascinating possibility about what infinity might mean for the universe. Maybe the universe is infinite, not just in the three spatial dimensions we experience, but in additional dimensions as well. Most of string theory requires 10 or 11 dimensions total, with the extra dimensions either curled up small or extended large. If those extra dimensions are infinite, then the universe is infinite in ways we can't even see or access directly. There could be infinite space perpendicular to our reality, dimensions of extension that we're completely blind to because we're confined to a three-dimensional brain floating in the higher dimensional bulk. This is wildly speculative, of course. We have no direct evidence for extra dimensions. But the mathematics of string theory seems to require them, and various experiments have looked for signs of their existence, so far without success. If they exist and are infinite, it would mean that the true dimensionality of reality is far stranger than we imagine. We'd be living in an infinite universe that's infinite in multiple ways simultaneously, extended without limit in directions we can't even point to. Let's think about the structure of an infinite universe for a moment, because infinity doesn't mean uniformity. Just because something goes on forever doesn't mean it's the same everywhere. In fact, an infinite universe could have infinite variety, infinite diversity of structure and composition. The part of the universe we can observe appears relatively uniform at the largest scales. We see the same types of galaxies, the same clustering patterns, the same overall density of matter and energy. But that uniformity only extends as far as we can see, about 93 billion light years. Beyond that, we simply don't know. It's entirely possible that the universe has large-scale structure that dwarfs anything we've observed. Maybe there are supervoids billions of light years across, regions where there's almost no matter at all. Maybe there are superclusters so massive they make the Laniakea supercluster, our cosmic neighborhood containing about 100,000 galaxies, look tiny by comparison. Maybe there are regions where the density of dark matter is different, where galaxies form differently, where the cosmic web has a completely different architecture. We wouldn't know. We couldn't know. Those structures would be beyond our horizon, invisible to us forever. And this is where the question of infinity intersects with the question of our uniqueness. If the universe is infinite and varied, then somewhere out there, beyond the reach of any observation, there are regions unlike anything we've seen. Regions where the laws of physics, or at least the effective laws that emerge from the fundamental ones, are different. This isn't as crazy as it sounds. The laws of physics as we experience them might be emergent properties that depend on local conditions. Things like the masses of particles, the strengths of forces, even the number of spatial dimensions that are accessible, these could be environmental features rather than fundamental constants. In the landscape picture of string theory, there are an enormous number of possible vacuum states, different ways the universe can settle into a stable configuration. Some estimates put the number at 10 to the 500 or more. Each vacuum state has different properties, different particle masses, different force strengths. If the universe is infinite and underwent eternal inflation, different regions could have settled into different vacuum states. Some regions would be like ours, with physics that allows for stable atoms and chemistry and life. Other regions would be sterile, unable to support complexity, and the vast majority would be somewhere in between, with properties we can't even imagine because they're so unlike our local physics. This is sometimes called the anthropic principle at work. We observe the universe to have properties that allow for our existence, because if it didn't have those properties, we wouldn't be here to observe it. It's a selection effect. If the universe is infinite and varied, then somewhere in its vastness there have to be regions like ours. And naturally, that's where we find ourselves. We couldn't exist in the sterile regions, so we don't observe them. We're necessarily in a habitable patch, a cosmic oasis where the conditions are just right for stars and planets and life to emerge. But this raises a troubling question about probability and prediction. If the universe is infinite and varied, with every possible configuration occurring somewhere, then almost anything we observe becomes equally likely. Why do we observe this particular set of physical constants rather than some other set? The anthropic answer is that we need these constants to exist, but that doesn't really explain why these specific values rather than other values that would also permit life. And if every possibility occurs somewhere in an infinite universe, how do we make predictions? How do we do science if every outcome is realized? This is an active debate in cosmology and philosophy of science. Some physicists argue that the anthropic principle is a cop-out, a way of giving up on finding deeper explanations. Others argue it's a legitimate recognition of selection effects, and that we need to take it seriously when dealing with infinite or near-infinite multiverse scenarios. The truth is probably somewhere in between. The anthropic principle can explain some things, but not others. It can explain why we observe a universe old enough for stars to form, because younger universes wouldn't have observers. But it can't explain specific details that don't affect habitability. Those details still need physical explanations. And this brings us to an important point about what we mean when we ask if the universe is infinite. Are we asking a purely geometric question about spatial extent? Or are we asking a deeper question about the diversity and richness of reality? Because those are related but different questions. A universe could be spatially infinite, but completely uniform, the same everywhere you look. Or it could be spatially finite, but contain within it an infinite diversity of structures or possibilities. The quantum many-worlds interpretation, for instance, posits an infinite number of branches, even if each branch is spatially finite. So maybe the right question isn't just whether the universe is infinite in size, but whether reality itself is infinite in its possibilities and manifestations. And that's a question that touches on metaphysics as much as physics. What is real? Is only the observable universe real, the part we can see and measure? Or is everything that's mathematically consistent and causally possible real, whether we can access it or not? These questions don't have easy answers, and different physicists and philosophers come down on different sides. David Deutsch, a quantum physicist and philosopher, argues that reality is much larger than the physical universe we observe. He claims that everything permitted by the laws of physics exists somewhere in the multiverse of quantum branches or cosmological regions. In this view, reality is infinite not just spatially but in structure space, the abstract space of all possible configurations and histories. Max Tegmark, another physicist, takes this even further, arguing that all mathematical structures exist as physical realities. If a mathematical structure is logically consistent, according to Tegmark, then it exists as a universe somewhere in the ultimate ensemble of all possibilities. This is sometimes called the mathematical universe hypothesis, and it implies a kind of infinity beyond infinity, an infinite tower of mathematical structures, each containing infinite elements. These ideas are fascinating but deeply controversial. Many physicists think they're unfalsifiable and therefore unscientific. If you can't test a hypothesis, if there's no observation that could prove it wrong, then maybe it's philosophy rather than physics. And maybe that's okay. Maybe there are questions at the boundary of our knowledge where science and philosophy blend together, where we can't fully separate what we observe from what we infer, what we know from what we speculate. But let's return to more concrete considerations, because there are observational programs that might give us hints about infinity, even if they can't prove it outright. One of the most interesting involves studying the topology of the universe. Even if the universe is spatially flat, as observations suggest, it could still have a non-trivial topology. Topology is about how space is connected, whether it wraps around on itself or has unusual structures like handles or twists. A flat universe could be infinite and simply connected, like an infinite plane, or it could be finite with a topology like a three-dimensional torus, where traveling far enough in any direction brings you back to your starting point. If the universe has a toroidal topology, we might be able to detect it by looking for repeating patterns in the cosmic microwave background. Light from the early universe would have traveled around the cosmos multiple times, creating circles in the sky where we see the same patches of the CMB from different angles. Astronomers have searched for these circles and haven't found them, which suggests that if the universe does wrap around, it does so on a scale larger than the observable universe. But the searches haven't ruled out all possible topologies. There are more exotic shapes, more complex ways space could be connected. That would be much harder to detect. Another way to probe infinity is through the spectrum of fluctuations in the cosmic microwave background. When we analyze the CMB, we break it down into different wavelengths of temperature variations. Most models of inflation predict that fluctuations should exist on all scales, but if the universe is finite, there should be a cutoff at the scale of the universe's size. We wouldn't see fluctuations larger than the whole universe because there's no room for them. Observations from Planck and WMAP have looked for this cutoff and found hints of something strange. The larger scale fluctuations seem weaker than expected, which could be evidence for a finite universe, or it could be a statistical fluke, or it could be telling us something else entirely about the inflationary process. The data isn't clear enough to draw firm conclusions yet. There's also the question of cosmic variance, the uncertainty in our measurements that comes from observing only one universe. If the universe is infinite and we're seeing only a finite patch, then our observations are subject to statistical fluctuations. We might happen to be in a region that's slightly denser or slightly less dense than average. We might see patterns in the CMB that aren't representative of the whole. This cosmic variance puts limits on what we can learn from observations, fundamental limits that no improvement in our instruments can overcome. We're stuck with a sample size of one observable universe, and that means there's always going to be uncertainty about the global properties of the cosmos. But maybe there are ways around this. Some cosmologists have proposed that we might be able to infer global properties from local observations by using sophisticated statistical techniques. If we understand the physics well enough, we can model what the universe should look like on large scales and compare that to what we see locally. Deviations from the predictions might tell us something about the global structure. It's a bit like trying to figure out the size and shape of a lake by analyzing the ripples on its surface. It's not easy, but it's not impossible either. And then there are the philosophical considerations that never quite go away, no matter how much data we gather. If the universe is infinite, what does that mean for concepts like causality and determinism? In a finite universe, you can imagine, at least in principle, accounting for every particle, every field, every quantum state. The whole universe could be described, theoretically, by one enormous wave function or one complete set of initial conditions. But an infinite universe, how do you specify initial conditions for infinite space? How do you write down a wave function for infinitely many particles? These questions push against the limits of what our physical theories can handle. Some physicists argue that if the universe is infinite, we need to rethink our approach to cosmology entirely. We can't talk about the state of the whole universe because there's no whole to talk about. We can only describe local patches, regions within causal contact where events can influence each other. In this view, cosmology becomes less about understanding the universe as a totality and more about understanding the local structure and how it relates to the larger scale patterns we can infer. It's a humbler approach, but maybe a more realistic one. And what about causality itself? In a finite universe, there's a cosmic horizon beyond which events are causally disconnected from us. But in an infinite universe with accelerating expansion, driven by dark energy, there are regions we'll never be able to communicate with or affect, no matter how long we wait. Information can't travel faster than light. And with space expanding, distant regions are receding faster than light can close the gap. So even in an infinite universe, we're effectively isolated in a bubble, a causally connected region beyond which we have no influence and from which we can receive no signals. This has strange implications for concepts like free will and determinism. If there are infinite other regions of the universe that are causally disconnected from us, then whatever happens there has no bearing on what happens here. The determinism or indeterminism of events in those regions is, in a sense, irrelevant to our experience. We're isolated islands of causality in an infinite ocean of space, each island evolving according to its own local dynamics, with no way to affect or be affected by the others. But there's a subtlety here worth exploring. Just because regions are causally disconnected now doesn't mean they always were. In the early universe, before inflation, all the matter and energy we see was compressed into a much smaller region, potentially within causal contact. Inflation stretched that region to enormous size, larger than our current observable universe, and in the process created regions that are now causally disconnected but share a common origin. So in a sense, the universe has a memory, an initial state that set the conditions for all the regions that inflated from it. Those regions are no longer in contact, but they bear the imprint of their shared past. This is why the cosmic microwave background is so uniform. It's the afterglow of a time when the entire observable universe was small enough for different parts to communicate, to equilibrate, to reach the same temperature and density. After inflation, those parts flew apart and lost contact. but they retained the memory of that early uniformity. And if the universe is infinite, there are infinitely many such regions, each with its own patch of CMB, each inheriting the same initial conditions, but evolving independently thereafter. Now let's think about the role of quantum mechanics in all this, because quantum mechanics adds another layer of weirdness to the question of infinity. In quantum field theory, the vacuum isn't really empty. It's seething with virtual particles, fluctuations that pop in and out of existence on incredibly short timescales. These fluctuations are real in the sense that they have observable effects. They contribute to things like the Casimir effect, where two metal plates in a vacuum experience a tiny attractive force because the vacuum fluctuations between them are restricted compared to the fluctuations outside. And they contribute to the Lamb shift, a tiny change in the energy levels of atoms caused by the interaction with vacuum fluctuations. If the universe is infinite, there are infinite vacuum fluctuations happening everywhere all the time. And here's where it gets strange. Quantum fluctuations can, in principle, create anything, given enough time and space. The probability is usually vanishingly small, but with infinite space and infinite time, even the most improbable events become certainties. Somewhere in an infinite universe, a quantum fluctuation might spontaneously create a galaxy, or a planet, or a brain, complete with memories and thoughts that exists for a brief moment before dissipating back into the vacuum. This is the famous Boltzmann brain paradox, named after the 19th century physicist Ludwig Boltzmann. If the universe is infinite and will last forever, then random thermal or quantum fluctuations will eventually create every possible configuration of matter, including conscious observers. But there are vastly more ways to create a single disembodied brain with false memories than there are to create an entire consistent universe with a history. So statistically, if you're a random observer in an infinite universe, you're more likely to be a Boltzmann brain, a momentary fluctuation with delusional memories, than a real person with a real history. Obviously, this seems absurd. We don't think we're Boltzmann brains. We have continuity of experience, consistent memories, a universe that behaves predictably. But the paradox points to a real tension in our theories. If the universe is infinite in space and time, and if quantum fluctuations can create anything, then we need to explain why we observe an ordered cosmos rather than a random fluctuation. Various solutions have been proposed. Maybe the universe won't last forever in a state that allows fluctuations. Maybe dark energy will eventually decay, or the vacuum will change, eliminating the possibility of Boltzmann brains. Maybe our theories of quantum mechanics or thermodynamics need revision. Or maybe we need to rethink what we mean by probability in an infinite universe. This gets at a deep problem with reasoning about infinities. When you have infinitely many things, ratios and probabilities become ill-defined. If there are infinitely many Boltzmann brains and infinitely many real observers, what's the ratio between them? Infinity divided by infinity isn't a meaningful quantity. You can't just count up the brains and the observers and compare. You need some way to regulate the infinities, some cutoff or measure that tells you how to weight different possibilities. And different choices of measure can give you radically different answers about what's typical or likely. This is an ongoing area of research in cosmology, and it's closely tied to the question of how to do science in a multiverse or infinite universe. If every possibility occurs somewhere, how do you make predictions? How do you say one theory is better than another? Normally in science, you compare theories by their predictions. The theory that predicts the observations more accurately is the better theory. But in an infinite universe, every theory might be correct somewhere. The theory that predicts Earth is flat is correct in some region where a flat Earth exists. So what does it mean to test theories? The answer, most physicists think, is that you need to be careful about what you're predicting. You're not predicting what exists in the universe as a whole, because everything exists somewhere. You're predicting what's typical or what you're likely to observe, given that you're a random observer. This involves statistical reasoning about the distribution of different types of observers across the infinite cosmos. And that requires making assumptions about how to count observers, which is exactly where the measure problem comes in. Different measures give different answers, and we don't have a clear, principled way to choose between them. Some physicists, like Sean Carroll, argue that we should take seriously the idea that probability is fundamental to cosmology, that we need a quantum mechanical description of the entire universe to make sense of these questions. In this view, the universe is described by a wave function that assigns amplitudes to different configurations, and those amplitudes determine what observers typically see. But applying quantum mechanics to the universe as a whole is fraught with difficulties. Who's measuring the universe? What does it mean for the wave function to collapse if there's no external observer? These are deep questions in quantum foundations that don't have agreed upon answers. Others, like Roger Penrose, are skeptical of the whole infinite multiverse framework. Penrose argues that we should favor theories that make definite predictions about what we observe rather than theories that allow everything to happen somewhere. He's proposed his own cosmology, conformal cyclic cosmology, where the universe goes through infinite cycles of expansion, but each cycle is finite and has definite properties. In Penrose's model, the infinite past and future don't lead to Boltzmann brain problems because each cycle resets the thermodynamics and structure. And this diversity of views among leading physicists tells you something important. The question of whether the universe is infinite isn't settled. It might never be fully settled. But the fact that we can ask the question rigorously, that we can frame it in terms of observations and theories, that we can debate the implications and explore the mathematical structures involved, this is a triumph of human thought. We've taken a question that was once purely philosophical and made it scientific, or at least scientific enough that we can make progress on it. Let's shift gears and think about what infinity means for the future of civilization, if there is one. If the universe is infinite, then there's infinite space to explore, infinite resources to utilize, infinite possibilities for growth and expansion. But there's a catch, and it's a big one. The universe is expanding, and the expansion is accelerating. That means the regions we can reach are limited, not by the infinity of space, but by the finite speed of light and the rate of expansion. There's a cosmological horizon beyond which galaxies are receding faster than we can ever catch up to them, even if we traveled at the speed of light. Our future light cone, the region of space-time we can ever influence or reach, is finite, even in an infinite universe. We're trapped in a bubble, a causally connected region that contains a finite number of galaxies, roughly a few 100 billion at most. Everything beyond that is forever out of reach. So even if the universe is infinite, from a practical standpoint, we're limited to a finite domain. That's our cosmic endowment, the total resources available to any civilization that might arise in our region. And those resources, while vast by human standards, are still finite. There are only so many stars, so many planets, so much energy available. Over cosmological timescales, trillions of years, even those will be exhausted. Stars will burn out, black holes will evaporate. The usable energy in our cosmic neighborhood will dwindle to zero. So infinity, in this case, doesn't save us from the heat death I mentioned earlier. It just means the heat death happens in our local bubble, while the rest of the infinite universe continues, inaccessible and irrelevant to our fate. But maybe there are ways around this. Some physicists have speculated about the possibility of creating new universes, baby universes that bud off from our own through quantum processes or black hole formation. If that's possible, and it's a huge if, then a sufficiently advanced civilization might be able to escape the heat death by engineering a transition to a new universe with fresh resources and energy gradients. This is wildly speculative, bordering on science fiction, but it's not ruled out by any known physical laws. It's the kind of thing that might be possible in principle, even if we have no idea how to do it in practice. And there's another possibility, equally speculative but intriguing. If the universe is infinite and eternal inflation is correct, then new big bangs are happening all the time, creating new regions of space with fresh initial conditions. Each inflating region is causally disconnected from the others, separate bubble universes in the eternally inflating multiverse. Maybe there's a way to navigate between these bubbles to find a path through the higher dimensional bulk that connects different regions. Again, this is pure speculation, but it's the kind of speculation that infinite cosmology allows. The point is, infinity opens up possibilities that don't exist in a finite universe. Not practical possibilities necessarily, but conceptual ones. It expands the space of what might be real, what might be achievable, what might exist beyond the limits of our current understanding. And that's valuable, even if we never actually encounter these infinite realms, because thinking about infinity stretches our minds, challenges our assumptions, forces us to confront the limits of our intuition and the edges of our theories. And maybe that's the real value of asking whether the universe is infinite. Not the answer itself, which we might never know for certain, but the process of asking, the journey of exploration and reasoning and imagination. Because in grappling with infinity, we're grappling with the most extreme possibilities reality can offer. We're pushing our concepts to their limits, testing whether our mathematics and physics can handle the ultimate extensions of space and time and possibility. And in doing so, we're learning something profound about ourselves and our place in the cosmos. We're learning that we're part of a reality that's vastly larger than us, possibly infinite, definitely incomprehensible in its totality. We're learning that the universe doesn't owe us answers, doesn't conform to our preferences, doesn't care whether we understand it or not. It simply is what it is, whatever that is. And our job as conscious beings, as the universe's way of knowing itself, is to do our best to figure it out, to ask the hard questions, to follow the evidence wherever it leads, and to be honest about what we don't know. The universe might be infinite. That's the simplest interpretation of the data we have. A flat geometry, cosmic uniformity, the theory of inflation, all point toward an infinite cosmos extending forever in all directions. But we can't be certain. We're limited by what we can observe, constrained by the horizons imposed by light speed and cosmic expansion. We're finite beings trying to comprehend the infinite, and there's a beautiful irony in that, a poignant futility mixed with stubborn determination. We'll keep measuring, keep theorizing, keep pushing the boundaries of knowledge. Maybe we'll find evidence that settles the question one way or the other. Maybe we'll discover that the universe has a subtle curvature we hadn't detected, indicating it's finite after all. Or maybe we'll find signatures of eternal inflation or quantum branching that make infinity unavoidable. Or maybe the question will remain perpetually open, a mystery at the heart of existence that we acknowledge but can't resolve. And you know what? That would be okay. Not every question needs an answer. Not every mystery needs to be solved. There's something beautiful about living with uncertainty, about accepting that there are limits to what we can know while still pushing against those limits. The universe is what it is, and our understanding of it is always provisional, always incomplete, always subject to revision in light of new evidence. But that doesn't diminish the value of the quest. If anything, it enhances it. Because we're not just accumulating facts and figures, we're participating in an ancient human tradition, the tradition of looking up at the sky and wondering what's out there, how it all works, why it's the way it is. We're asking the big questions, the questions that define us as a species, that separate us from other animals, that give meaning to our brief flicker of consciousness in a vast and possibly infinite cosmos. So yes, the universe might be infinite. It might extend forever, filled with infinite galaxies and infinite stars and infinite possibilities. Or it might be finite but unimaginably vast, larger than we can measure but still bounded in some way we don't understand. Either way, it's a cosmos of extraordinary richness and complexity, a place where the improbable becomes inevitable given enough space and time, where consciousness emerges from matter and contemplates its own origins, where questions about infinity can be asked and partially answered and endlessly pondered, and we're part of it. Not separate observers looking at the universe from outside, but embedded participants, beings made of the same stuff as stars, governed by the same laws, shaped by the same cosmic history. When we ask if the universe is infinite, we're really asking about the nature of reality itself, about what exists and how much of it exists, and whether there's a totality or just endless extension. These are questions at the intersection of physics and philosophy, science and spirituality, knowledge and wonder. And maybe that's where they should stay, not definitively answered, but held in creative tension, explored from multiple angles, approached with both rigor and humility, because infinity is more than a mathematical concept or a cosmological parameter. It's a symbol of the unknowable, the unreachable, the forever beyond. It represents everything that lies outside our grasp, beyond our horizon, past the limits of measurement and inference. And in confronting infinity, we confront our own finitude, our own smallness, our own temporary existence in a universe that was here long before us and will be here long after. But we also confront our own significance, paradoxically, because even though we're tiny compared to the cosmos, even though we're brief compared to cosmological time, we're the part of the universe that can ask these questions, that can build telescopes and satellites and theories, that can measure and calculate and wonder. We're how the universe knows itself. And in an infinite cosmos, that might be infinitely rare, or it might happen infinitely often. We don't know. But it's happening here now, in this corner of space at this moment in time. And that's something. That's everything, really. So when you look up at the night sky and feel small, remember that you're also large. You contain multitudes, as the poet said. Your brain has more connections than there are stars in the galaxy. Your thoughts emerge from quantum processes and chemical reactions and electrical impulses, all orchestrated in ways we're only beginning to understand. You're a miracle of complexity and organization, a temporary eddy in the flow of entropy, a brief pattern that arose from chaos and will eventually return to it. But while you exist, you're as real and significant as anything in the universe. And when you wonder how far the universe extends, remember that wondering is itself a kind of answer. Not an answer to the question of infinity, but an answer to the question of meaning. Why are we here? What's the point of existence? Maybe the point is the asking, the wondering, the endless curiosity that drives us to explore and understand. Maybe the universe doesn't have a purpose in the grand cosmic sense, but we can create purpose through our choices and actions and relationships and quests for knowledge. And one of those quests is understanding the cosmos itself, figuring out whether it's infinite or finite, whether we're alone or part of an infinite multiplicity of worlds and possibilities. The universe might be infinite. And if it is, that means we're living in a reality more vast and strange and beautiful than anything our ancestors could have imagined. A reality where space extends without limit, where time unfolds without end, where possibilities multiply beyond counting. A reality where the word all doesn't capture everything, because there's no everything, just endless more. A reality where every question we answer opens up new questions, where every horizon we reach reveals new horizons beyond, where the journey of understanding never ends, because there's always more to understand. And that, I think, is the most profound implication of an infinite universe. Not that we're insignificant, not that nothing matters because everything exists somewhere, but that there's always more to discover, more to explore, more to wonder about. The universe, if it's infinite, is an inexhaustible source of mystery and beauty and complexity, and we, tiny and brief as we are, get to be part of that. We get to ask the questions, chase the answers, marvel at the discoveries. We get to be the universe's way of comprehending itself, of reaching toward understanding, of touching the infinite with finite minds. So maybe the answer to whether the universe is infinite doesn't matter as much as the asking. Maybe what matters is that we're here now, capable of asking, driven to ask, compelled by our nature to seek understanding, even when the questions are too large to fully grasp. The universe has given us this gift, this capacity for wonder and reason and imagination. And in return, we give the universe something it couldn't have without us: a witness, a contemplator, a consciousness that looks out at the stars and asks how far they go and why and what it all means. That's what we are, that's what we do. And whether the universe is infinite or finite, that's enough. That's more than enough. It's everything. And yet there's still more to explore here, more angles to consider, more depths to plumb, because when we talk about the universe being infinite, we haven't fully grappled with what that means for some of the most basic concepts we take for granted, like identity and uniqueness. If the universe is truly infinite and contains infinite instances of every possible configuration, then what does it mean to be you? What makes you distinct from all those other versions of yourself scattered across the infinite cosmos? This isn't just a philosophical puzzle. It touches on questions of consciousness and personal identity that philosophers have debated for millennia. Are you the same person you were 10 years ago? Your cells have been replaced, your memories have changed, your personality has evolved. What makes you continuous with that past self? Usually we appeal to psychological continuity, the thread of memory and experience that connects your present self to your past selves. But in an infinite universe with infinitely many identical copies of you, that criterion breaks down. There are other beings with exactly the same memories, exactly the same experiences, exactly the same psychological continuity. Are they you, or are they different people who just happen to be indistinguishable from you? One way to think about this is through the lens of indexical information. The philosopher David Lewis argued that what makes you unique isn't just your properties, but your location in space-time. You're this person here, now. The fact that there might be duplicates elsewhere doesn't change the fact that you're specifically located in this region of space at this moment in time. Your identity is bound up with your particular spatiotemporal location, not just your intrinsic properties. So even if there are exact copies of you infinitely far away, they're not you because they're not here. They're there wherever there is. But this raises its own puzzles. If identity depends on location, and space is infinite and homogeneous, then what makes your location special? From a global perspective, no location is privileged. Every point in an infinite universe is equally central, equally peripheral, equally arbitrary. So maybe identity isn't about location after all. Maybe it's about something else, something we haven't quite put our finger on yet. Maybe it's about the specific causal history that led to you, the unique chain of events that resulted in your existence here and now. Even if someone elsewhere has the same memories and properties, they don't have the same causal past. Their atoms came from different stars, their planet formed from a different protoplanetary disk, their evolution followed a different random path, even if it ended up at the same destination. And this connects to another fascinating implication of infinity, the question of determinism and free will. If the universe is infinite and every possible outcome occurs somewhere, then in what sense are your choices free? There's a version of you that chose differently, and another version, and another, infinitely many versions making every possible choice. Does that mean your choices aren't really yours, that you're just playing out one of infinitely many predetermined scripts? I don't think so. The existence of other versions doesn't change the fact that you're making choices based on your values, your reasoning, your preferences. You're not aware of those other versions. They don't influence your decision-making. From your subjective perspective, from the inside, your choices are yours. You deliberate, you weigh options, you commit to a course of action. The process is real even if the outcome is replicated elsewhere. And in fact, the existence of all those other versions might even enhance your freedom in a strange way. It means that no matter what you choose, some version of you chose it. Every possible path is actualized somewhere. There's a version of you that made the brave choice, the cautious choice, the creative choice, the practical choice. All of them exist, all of them are real, and the one you're living through is uniquely yours. But let's dig into the physics again, because there's a crucial aspect of infinity we haven't fully explored, the role of quantum mechanics at cosmological scales. We've talked about quantum fluctuations and the many worlds interpretation, but there's more to say about how quantum mechanics interacts with an infinite universe. In quantum field theory, the vacuum state, the state of lowest energy, is defined across all of space. But if space is infinite, what does it mean to have a vacuum state? Can you have a quantum field that extends infinitely? What's the total energy of an infinite quantum field? These questions lead to technical challenges in quantum field theory. Normally, physicists deal with them by working in finite volumes and then taking limits as the volume goes to infinity. But that's a mathematical trick, a way of handling infinities in calculations. It doesn't tell us what's really going on physically. If the universe is actually infinite, not just in some limiting sense, but literally, then we need to make sense of quantum fields on infinite space directly. And that's hard. It raises issues about normalization, about how to define probabilities, about how to count states. Some physicists argue that quantum field theory needs to be reformulated for truly infinite systems. Others think the existing framework is adequate if you're careful about how you apply it. But everyone agrees that combining quantum mechanics with infinite space is subtle and requires careful thought. You can't just take the finite space formulas and plug in infinity. That leads to nonsense, infinities that can't be removed by renormalization techniques. You need a more sophisticated approach, one that respects both the quantum nature of fields and the infinite extent of space. and this connects to the measurement problem in quantum mechanics, one of the deepest unresolved questions in physics. When you make a measurement, the quantum wave function collapses from a superposition of possibilities to a definite outcome. But what causes this collapse? Is it a real physical process, or is it just our ignorance about which branch of the wave function we're on? And if it's real, how does it work in an infinite universe? Does the wave function collapse everywhere at once, or does the collapse propagate at the speed of light? If collapse is instantaneous across infinite space, that seems to violate relativity. If it propagates, then distant regions remain in superposition while nearby regions collapse. And how do you reconcile that with a unified description of the universe? The many worlds interpretation offers one solution. There's no collapse. The wave function keeps evolving unitarily, splitting into branches where every outcome occurs. In this view, an infinite universe becomes even more infinite because you're multiplying the infinite space by the infinite branching of quantum possibilities. It's infinity times infinity, a higher order of infinity in some sense, though mathematically it's still just countable infinity if the branching is discrete. But conceptually, it's staggering. Every quantum event in every region of infinite space creates new branches. And this has been happening since the Big Bang, creating a tree of realities that grows incomprehensibly complex with each passing moment. Or maybe the collapse is real, but it's a local phenomenon. When you make a measurement here, the wave function collapses in your local region, but distant regions, light years away, remain in superposition until someone there makes a measurement. This is sometimes called the objective collapse theory, and there are various versions of it, each with different mechanisms for what causes collapse. Some involve gravity, the idea that when matter reaches a certain density or complexity, it triggers a collapse. Others involve new physics, undiscovered fields or interactions that mediate the collapse process. None of these theories are fully developed or widely accepted, but they represent active areas of research in quantum foundations. And here's where it gets really interesting. If collapse is real and local, then an infinite universe could be in different quantum states in different regions. Some regions might be in a superposition that collapsed one way, others in a superposition that collapsed differently. And because those regions are causally disconnected, there's no contradiction. The universe as a whole doesn't have a definite quantum state. Only local regions do. It's like each causally connected patch of the universe has its own quantum description, and the global picture is an infinite collection of these local descriptions, each evolving independently. This is a radically different way of thinking about quantum mechanics and cosmology. Instead of trying to describe the wave function of the entire universe, which might be impossible if the universe is infinite, you focus on local wave functions that describe causally connected regions. And you accept that there's no global quantum state, no single wave function that captures everything. It's a more modest approach, but maybe a more realistic one. Let me take you in another direction now, because there's a historical dimension to the question of infinity that's worth exploring. The idea that the universe might be infinite isn't new. Ancient Greek philosophers debated it. Epicurus and his followers believed in an infinite cosmos, filled with infinite worlds, each with its own sun and planets. They arrived at this conclusion not through observation, but through philosophical reasoning. If the universe had an edge, what would be beyond the edge? And if there's something beyond, then the edge wasn't really the edge, so the universe must extend forever. It's a logical argument, and while it doesn't prove infinity, it shows that people have been grappling with this question for thousands of years. In the medieval period, the question took on theological dimensions. Christian philosophers debated whether God could create an infinite universe. Some, like Thomas Aquinas, argued that while God is infinite, creation must be finite because only God can be truly infinite. To claim the universe is infinite would be to put it on par with God, which is heretical. Others argued that God's power is unlimited, so of course God could create an infinite universe if God chose. These debates weren't just about theology. They were about the nature of infinity itself, whether it's a coherent concept, whether it can exist in physical reality or only in the mind of God. The scientific revolution changed the terms of the debate. When Copernicus dethroned Earth from the center of the cosmos, it opened up the possibility that the universe is much larger than previously thought. Giordano Bruno went further, arguing that the universe is infinite and filled with infinite stars and worlds. He was burned at the stake for this and other heresies, though it's not clear how much his cosmology contributed to his execution. Still, his vision of an infinite cosmos was radical for its time, and it anticipated later discoveries about the scale of the universe. Newton's physics provided a framework for understanding an infinite cosmos. Newtonian gravity works the same whether the universe is finite or infinite. In fact, Newton worried about the stability of an infinite universe. If space is filled with stars distributed uniformly, each star would be pulled equally in all directions by the gravitational attraction of distant stars, leading to a kind of equilibrium. But any small perturbation would cause the stars to collapse together because there's no restoring force. This is one of the first examples of using physics to constrain cosmology, to ask what kind of universe is consistent with the laws of nature. Einstein's general relativity changed everything again. In general relativity, the geometry of space is determined by the distribution of matter and energy. Einstein initially believed the universe must be static, neither expanding nor contracting, and he added a cosmological constant to his equations to achieve this. But his static universe turned out to be unstable, and observations by Hubble showed that the universe is expanding. This led to the Big Bang theory and a new understanding of cosmic history. And it raised the question of infinity in a new form, not whether space is infinite, but whether it was always infinite or became infinite through expansion. As we've discussed, modern cosmology suggests that if the universe is flat, it's likely infinite. But the history shows that our understanding of infinity has evolved along with our physics. Each new theory, each new set of observations has refined our thinking about what infinity means and whether it applies to the cosmos. And we're still in the middle of that evolution. Future discoveries might change our understanding again, might reveal aspects of the universe we haven't imagined. Let's think about the practical implications of an infinite universe for astronomy and exploration. If the universe is infinite, there are infinitely many galaxies to observe, infinitely many stars to study, infinitely many planets to discover, but we're limited by our cosmic horizon. We can only see galaxies whose light has had time to reach us since the Big Bang. And as the universe expands and accelerates, that horizon is effectively shrinking in terms of new galaxies we can observe. Galaxies that are currently beyond our horizon will never become visible, no matter how long we wait. Their light will never reach us because space is expanding too fast. This means that future astronomers will have access to less information about the universe than we do today. In a way, we're living in a golden age of cosmology, a time when we can still see evidence of the Big Bang and the large-scale structure of the cosmos. Billions of years from now, if civilizations still exist, they'll look out and see a much emptier sky. The cosmic microwave background will be redshifted into invisibility. Distant galaxies will have disappeared beyond the horizon. Future scientists might conclude that their galaxy is alone in an empty, expanding space. They'd have no way to know about the Big Bang, no way to infer that there were once billions of other galaxies, no way to discover the true nature of the cosmos. This is a sobering thought. It means that knowledge isn't cumulative in the way we usually think. It's not that each generation builds on the discoveries of the previous generation, creating an ever-growing edifice of understanding. Instead, there are windows of opportunity, periods when certain types of observations are possible, and outside those windows, the information is lost forever. We're lucky to be living in a time when the universe is still young enough, still observable enough that we can piece together its history and structure. But that luck won't last forever. And this raises ethical questions about our responsibility to future generations. Should we be doing everything we can to record and preserve our observations of the cosmos while we still can? Should we be building archives of astronomical data that will outlast our civilization so that if anyone comes after us, they'll have access to this information? These might seem like abstract concerns, but they're real. If we don't preserve what we're learning now, it will be lost. And future intelligences, if they exist, will be impoverished for it. There's also the question of what we might discover if we keep looking. If the universe is infinite, there's always more to find. Every time we build a more powerful telescope, we see farther and deeper. We discover new types of objects, new phenomena, new structures, quasars, pulsars, black holes, dark matter, dark energy, gravitational waves. All of these were unknown a century ago. What else is out there waiting to be discovered? What strange objects and forces and patterns might exist beyond our current observational reach? An infinite universe guarantees that there are surprises ahead. Not just more of the same, but genuinely new things, phenomena that don't occur in our local region, or are so rare that we haven't encountered them yet. Maybe there are stars made of dark matter. Maybe there are regions where the laws of physics are subtly different, where particles have different masses or forces have different strengths. Maybe there are structures on scales larger than galaxy superclusters, patterns and organizations that only become apparent when you zoom out far enough. We can't know until we look. And in an infinite universe, we can never finish looking. There's always another horizon, another scale, another mystery. But here's a paradox. If the universe is infinite and homogeneous, then looking farther shouldn't reveal anything fundamentally new. Every region should be statistically similar to every other region. The same types of galaxies, the same clustering patterns, the same distributions of matter and energy. So how can there be surprises? How can an infinite, homogeneous universe contain novelty? The answer is that homogeneity is a statistical property. On average, at large scales, the universe looks the same everywhere. But there are fluctuations, variations, rare events. And in an infinite universe, even the rarest events occur infinitely many times. So somewhere out there, there's a galaxy cluster that's twice as massive as any we've seen. Somewhere there's a black hole that's 1 trillion times the mass of the sun. Somewhere there's a region where the density fluctuations in the early universe happen to create a structure unlike anything in our observable patch. These things are rare, maybe vanishingly rare, but in infinity, they're guaranteed to exist. And that means there's always something new to discover if we look far enough or wait long enough. The universe is infinite, but it's also full of variation. It's uniform on average, but rich in detail. And that combination, uniformity plus variation extending infinitely, is what makes cosmology endlessly fascinating. You can never see it all, never catalogue it all, never understand it all. There's always more. Now let's consider the role of symmetry in an infinite universe. Symmetries are fundamental to physics. They tell us that the laws of nature are the same everywhere and at all times. Translational symmetry means the laws don't change if you move to a different location. Rotational symmetry means they don't change if you rotate your coordinate system. Time translation symmetry means they don't change as time passes. These symmetries are deeply embedded in our theories, and they have profound consequences. Noether's theorem tells us that every continuous symmetry corresponds to a conservation law. Energy is conserved because the laws of physics don't change over time. Momentum is conserved because they don't change with position. Angular momentum is conserved because they don't change with orientation. But in an infinite universe, some of these symmetries become subtle. Take translational symmetry. If the universe is infinite and homogeneous, then moving to a different location shouldn't change anything. But if the universe has structure, variations in density and composition, then different locations are different. How do you reconcile this with translational symmetry? The answer is that the symmetry is statistical. On average, over large volumes, the universe looks the same at different locations. But locally, there are variations. Your location matters because it determines your local environment, even though globally, no location is special. And this has implications for how we think about the laws of physics in an infinite universe. Are the laws truly universal, the same everywhere across infinite space? Or could they vary in ways we haven't detected? We've tested the laws of physics in our solar system, in our galaxy, in nearby galaxies, even in distant galaxies billions of light years away. And as far as we can tell, they're the same everywhere. The spectral lines of hydrogen in a distant galaxy match the spectral lines of hydrogen in our labs. The fine structure constant, which determines the strength of electromagnetic interactions, seems to be the same in all the galaxies we've observed. but we've only sampled a tiny fraction of the universe. If space is infinite, there could be regions where the laws are different, and we'd never know because those regions are beyond our horizon. Or maybe the laws are truly universal, encoded in the fundamental structure of reality in a way that doesn't allow for variation. This is another open question, another uncertainty at the edge of our knowledge. Let's talk about entropy now, because entropy is central to understanding the evolution of an infinite universe. The second law of thermodynamics says that entropy, roughly speaking disorder, always increases in a closed system. But what does closed system mean if the universe is infinite? Can an infinite universe be closed? Does entropy still increase? And if so, what does maximum entropy look like in an infinite system? These are tricky questions. In a finite universe, maximum entropy corresponds to heat death, a state of uniform temperature and density where no energy gradients exist to drive any processes. Everything reaches thermal equilibrium and nothing interesting happens ever again. But in an infinite universe, it's not clear what maximum entropy means. You can't just add up the entropy of all the infinite regions because you get infinity. So how do you define whether entropy is increasing? One approach is to look at entropy density, entropy per unit volume. In an expanding universe, entropy density can decrease even as total entropy increases because the volume is growing faster than the entropy. This is what's happening in our universe right now. The early universe was extremely hot and dense with high entropy density. As it expanded and cooled, the entropy density decreased even though the total entropy increased. This seems to violate the second law, but it doesn't because the universe isn't a closed system in the usual sense. It's expanding, and that expansion changes the game. But over very long timescales, as the expansion continues and accelerates, the entropy density will approach a constant value determined by the temperature of the cosmic event horizon. This is called de Sitter space, a space-time with a cosmological constant that creates a kind of equilibrium temperature. And in de Sitter space, the entropy is finite, even though the space itself extends infinitely. The entropy is associated with the horizon, not with the volume of space. This is one of the deep insights from black hole thermodynamics, the idea that entropy can be associated with boundaries and horizons rather than bulk regions. So, in a sense, even an infinite universe has finite entropy, at least the entropy that's accessible to any given observer. You can only interact with the regions within your cosmic horizon, and that horizon has a finite entropy. Everything beyond the horizon is causally disconnected from you, so its entropy doesn't matter for your local physics. This is a strange but profound result. It suggests that finiteness emerges from infinity in unexpected ways, that even though the universe might be spatially infinite, the information content and entropy relevant to any observer is finite. And this connects to the holographic principle, one of the most radical ideas in modern theoretical physics. The holographic principle says that all the information in a volume of space can be encoded on the boundary of that volume like a hologram. A three-dimensional image can be stored in a two-dimensional surface. Applied to cosmology, this suggests that all the physics inside your cosmic horizon can be described by degrees of freedom on the horizon itself. The universe might be a kind of hologram, a three-dimensional projection of information encoded on a two-dimensional surface. If this is true, and it's still speculative, then the infinity of space might be an illusion in some sense. The fundamental description of the universe might involve a finite number of degrees of freedom on the horizon, and the infinite space we perceive might emerge from that finite description. This is deeply weird, and it challenges our intuitions about what's real and what's fundamental. But it's taken seriously by many physicists because it resolves certain paradoxes and unifies aspects of quantum mechanics and gravity. Let's bring this back to something more concrete. The question of whether we'll ever know for certain if the universe is infinite. As I've mentioned, there are fundamental limits to what we can observe. We can't see beyond our cosmic horizon. We can't directly measure the curvature of space on scales larger than the observable universe. We can't verify whether the universe continues uniformly beyond what we can see, or if there are variations and surprises out there. But maybe there are indirect ways to test infinity. Maybe the quantum state of the early universe, if we could fully reconstruct it, would tell us something about the global structure. Maybe gravitational waves from the inflationary epoch carry information about whether inflation was eternal or finite. Maybe there are subtle statistical signatures in the cosmic microwave background that reveal the topology of space or the total volume of the universe. These are long shots and they might not pan out, but they represent avenues of research that could, in principle, give us more confidence one way or the other. And even if we can't prove infinity, we can constrain it. We can say things like, if the universe is finite, it must be at least this big. Or, if it's closed, the curvature must be less than this amount. And those constraints are valuable. They narrow down the possibilities. They tell us what's consistent with observations and what's ruled out. That's how science progresses, not always by finding definitive answers, but by ruling out wrong answers and refining the questions. There's also the possibility that future developments in physics will change how we think about infinity altogether. Maybe quantum gravity will reveal that space is fundamentally discrete, that there's a smallest possible unit, and infinity is just a mathematical idealization that doesn't apply to physical reality. Or maybe we'll discover that the universe is finite, but embedded in a larger structure, a multiverse or higher dimensional space, and the question of infinity shifts to that larger context. Or maybe we'll find that the question itself is ill-posed, that we're asking about something that doesn't have a well-defined answer in our theoretical framework. These possibilities remind us that our current understanding is provisional. We're working with the best theories we have, but those theories might be incomplete or approximate. General relativity and quantum mechanics are extraordinarily successful, but we know they're not the final word. They're incompatible with each other at the Planck scale, and we need a theory of quantum gravity to unify them. And that theory, when we find it, might tell us things about space and time and infinity that we can't even imagine with our current concepts. So where does all this leave us? We've journeyed through geometry and inflation, quantum mechanics and thermodynamics, philosophy and observation, history and speculation. We've explored what it would mean for the universe to be infinite, what evidence supports that possibility, what challenges it raises, what implications it has for our understanding of reality and our place in it. And after all that, the honest answer is still, we don't know for certain. The universe might be infinite. It might not be. Both possibilities remain open, consistent with what we've observed, defensible given our current theories. But what we do know is that the question matters. It matters for physics, for how we formulate our theories and make our predictions. It matters for philosophy, for how we think about existence and reality and meaning. And it matters for us, for how we see ourselves and our significance in the grand scheme of things. An infinite universe challenges us to think bigger, to imagine more, to accept that reality might exceed our grasp in fundamental ways. And maybe that's the takeaway. Not a definitive answer to whether the universe is infinite, but an appreciation for the question itself, for what it reveals about the human endeavor of understanding. We're creatures of finite lifespans and limited perception, trying to comprehend the ultimate nature of a cosmos that might be without limit. That's ambitious, it's audacious, it's beautiful. And the fact that we can even ask the question, that we can gather evidence and build theories and make progress toward an answer, that's a testament to the power of human thought and the reach of scientific inquiry. The universe might be infinite, extending forever in space, continuing endlessly in time, branching infinitely in quantum possibilities, repeating infinitely in cosmic variations. Or it might be finite but vast, bounded but immeasurable, limited but incomprehensible in scale. Either way, it's a cosmos of extraordinary richness, a place where the improbable becomes real, where consciousness emerges and contemplates its origins, where questions about infinity can be posed and partially answered. And we're here, in this moment, part of it all, made of star stuff, governed by natural laws, shaped by cosmic history, asking the big questions. The universe doesn't need us to understand it. It would continue existing whether we pondered its nature or not. But we need to ask. It's in our nature. We're the part of the universe that looks back at itself and wonders, how far do you go? What are you made of? Why are you the way you are? Are you infinite, or do you end somewhere beyond my sight? These questions define us. They elevate us. They connect us to every human who's ever looked up at the sky and felt that mixture of wonder and insignificance, that strange combination of being so small yet capable of such vast thought. We're brief sparks of awareness in a possibly infinite cosmos, and our brevity doesn't diminish our significance. If anything, it enhances it, because we're rare. Life is rare. Consciousness is rare, intelligence is rare, and the ability to ask whether the universe is infinite and to pursue that question with rigor and imagination and honesty, that's rarest of all. So yes, the universe might be infinite, and in contemplating that possibility, in wrestling with its implications, in pushing the boundaries of our knowledge and imagination, we're doing something profoundly human and profoundly meaningful. We're reaching toward the infinite with finite minds, and in that reaching, we're participating in one of the great adventures of consciousness, the universe exploring itself, reality wondering about its own nature, existence asking, am I without limit, or do I have an edge? And in the asking, in the seeking, in the endless quest for understanding, we find not just science but poetry, not just knowledge but wisdom, not just facts but meaning. And maybe that's enough, maybe that's everything. But let me leave you with one final thought, one last layer to consider. Because ultimately, the question of whether the universe is infinite isn't just about space or time or quantum mechanics or cosmology. It's about something deeper, something that touches on the very nature of knowledge and reality. It's about the relationship between what is and what we can know about what is. And that relationship, that gap between reality and our understanding of it, is itself infinite in a way. Think about it. Every answer we find opens up new questions. Every horizon we reach reveals new horizons beyond. Every mystery we solve shows us new mysteries we hadn't known existed. This is the history of science in microcosm. We thought the universe was just what we could see with our eyes. Then we built telescopes and discovered it was much larger. We thought our galaxy was the entire universe. Then we discovered billions of other galaxies. We thought space was static and eternal. Then we discovered it's expanding and had a beginning. Each revelation didn't close the book on our questions, it opened new chapters, and there's no reason to think this process will ever end. Even if we figure out whether the universe is spatially infinite, there will be other questions. What came before the Big Bang? What's the nature of dark energy? How does quantum mechanics really work? Are there other universes? Is there a theory of everything that unifies all the forces and explains all the particles? And when we answer those questions, assuming we can, there will be more questions beyond them. The frontier of knowledge keeps receding, always out of reach, always beckoning us forward. In that sense, the infinity that matters most isn't the infinity of space. It's the infinity of understanding, the endless depth of reality, the inexhaustible richness of the cosmos. Even if the universe is finite in size, it's infinite in the questions it poses, the phenomena it exhibits, the structures it contains, the stories it tells. You could study the universe forever and never run out of things to learn. You could explore it forever and never exhaust its wonders. That's a different kind of infinity, maybe even more profound than spatial infinity. And this infinity of understanding means that our quest for knowledge is never finished. We're never done. There's no final chapter where we understand everything and close the book. We're always in the middle of the story, always learning, always discovering, always revising our understanding in light of new evidence. And that's not a bug, that's a feature. Because a universe fully understood, a cosmos with no remaining mysteries, would be a poorer place. The mystery itself, the not knowing, the sense of wonder and possibility, that's part of what makes existence rich and meaningful. So when you ask whether the universe is infinite, remember that you're really asking about the nature of reality and our relationship to it. You're asking whether there are limits to what exists, and by extension, whether there are limits to what we can know. And the answer seems to be existence is larger than our knowledge, reality is richer than our theories, the cosmos is more complex than our models. Whether that means literally infinite or just effectively infinite from our perspective might not matter as much as we think. What matters is that we keep asking, keep exploring, keep reaching toward understanding even when the goal seems impossibly distant. What matters is that we don't give up in the face of mystery, don't close our minds to new possibilities. Don't settle for easy answers when the true answers might be difficult or uncomfortable or strange. What matters is that we honor the quest itself, the human drive to understand, to explain, to know. The universe might be infinite, and whether it is or isn't, whether we ever know for certain or remain forever uncertain, the journey toward understanding is what defines us. We're the species that looks at the stars and wonders. We're the consciousness that emerges from matter and asks questions about its own existence. We're the finite beings who contemplate infinity and find in that contemplation not despair at our limitations, but inspiration to keep reaching, keep learning, keep growing in our understanding. And that's the real answer to the question, not whether the universe is infinite, but what we do with the question, how we let it shape us, challenge us, motivate us, how we use it to push the boundaries of human knowledge and human imagination, how we honor the mystery even as we work to solve it. That's what it means to be conscious in a possibly infinite cosmos. That's what it means to be human in a universe we're only beginning to understand. And that's what makes the question of infinity not just a scientific puzzle, but a profound meditation on existence itself.